So good morning, everyone. Welcome to today's lecture recap. And as usual, I'm going to start with a quick review of what we were talking about last time. And that was the heat transferred out of an object due to radiation. So we understood that an object at any temperature will emit electromagnetic radiation in various wavelengths. And the amount of radiation at each of those wavelengths is going to change as we change the temperature. And in this slide, I've just taken a few screenshots from the video that I showed last time of an object. It was a nail. Here's actually a nail between two electrical contacts. And we put a very large current through the nail, allowed the nail to heat up, and eventually it started glowing as the temperature got to a certain point. And so we could see that the object got brighter and brighter and brighter as the temperature was increasing. And then because the light was actually passed through a prism before coming to the camera, it separated out a little bit into the various colors, with the red light going more towards the top of the screen and the blue light going more towards the bottom of the screen. And so you could actually see as we heat up, then also the colors that are present are changing. Originally, we couldn't see it at all since it's only infrared. Then we see some red, then red and orange, red, orange, yellow, green. And then by the end, when it was very, very hot, then you could see actually all of the colors in the visible spectrum. And so that reflected the fact that the spectrum of light from a hot object has a peak wavelength, which is shifting shorter and shorter as the temperature increases. Today, we're going to be focusing more on the other aspect, where the total radiation from the object is increasing with temperature. And the quantitative formula that's important for us is this one, where if I double the temperature, then the total heat current coming off of my object is going to increase by a factor of 16. So you have this very strong T to the fourth dependence in the heat current. The other thing that the heat current depends on is the surface area of your object. And so if you had an object with a similar material and the same surface properties, and then you just doubled the surface area, or considered another object that's the same in all ways except for the surface area, then the heat current is just going to be proportional to that area. So you could just think of each little part of the surface is going to emit radiation at a certain rate per area, which is determined by the temperature. And then to get the total rate, we just multiply by the area. Okay. Sigma is just a constant. It actually should be 5.67 times 10 to the minus 8. There's a typo there. The other constant coming into this formula is E, and that is something that depends on the properties of your surface. So it depends on, this is like the constant that depends on what actual material are you looking at. And in this case, it's actually a property of the surface of your material. So we talked about last time how if you had an object which is a perfect absorber, okay, so maybe a very black object that absorbs radiation perfectly, then this E is going to be equal to 1. That's actually the case also that produces the most radiation. And any other object is going to be producing an amount of radiation which is some fraction of that. Okay, so you could think of this number E as if you have two objects and one of them is a perfect absorber, so that will be producing the most radiation. If you have an other object given the same surface area and the same temperature, it will be producing some fraction of the amount of radiation compared with your perfect absorbing object, and that fraction is E. Okay, so now combining everything, this allows you to predict the total heat current coming off an object at various temperatures. So then we had some applications of that formula. And one of the key features of systems that maybe have been allowed to settle in for a while so that the temperatures of the various parts of the system are not changing, in those kinds of situations, which come up a lot in these heat conduction problems and the heat current problems and the radiation problems, there's a key idea that we're using over and over and over again. And so I wanted to formalize that by making it a formula on this slide. And so that is that if I have any part of my system and we're in a steady state situation where the temperature of that part is not changing with time, that means that the heat current into that part of the system has to equal the heat current out of that part of the system. So this is just a basic equation that applies whenever you have some steady state situation where the temperatures aren't changing. Okay. The reason is that if those were not equal, if the heat in was, say, greater than the heat out, then you would have energy building up in the object, and that would cause the temperature to increase. Okay. As an example, let me remind you of this question that we had last time, where we wanted to understand, make a prediction for how the surface temperature of this planet that this creature Yoltar lives on, how is that related to the energy put out by the core of the planet? Okay, this is some artificial core that we have. We can control the amount of power. We can control how much energy per time is coming out of the core. And so we wanted to understand, how does that affect the surface temperature of the planet? And so in order to solve that problem, we first made the assumption that we'd waited long enough so that we're in a steady state where the temperatures of the various parts of the planet have stabilized and are no longer changing with time. And then at that point, what we could say is that whatever energy goes out of the core also has to go out of the planet itself by radiation. Okay, so we're applying this Hn equals H out to the rocky material that this planet is made of. The H in is just the power of the heater, which, say, in this case is 1 gigawatt. And the H out is equal to the amount of heat current because of radiation. Okay, so this is just a planet out in empty space. There's no conductivity of heat into space. There's no convection because there's no molecules around the planet. It's just radiation. And so the H out is given by the A sigma E T to the fourth formula. Okay, so those have to be equal once we've settled down to a steady state, and then we can directly calculate the temperature of the surface in terms of the power of the heater. Okay. And so this was, I think the question was, what do you have to do to the power of the heater if you want to double the temperature of the surface? And from this formula, you need to multiply that power by 16. Someone asked in class, would you ever have a situation when Hn is not equal to H out? What would be an example of that? And so that would be, for example, if you started with a very cold planet and then you installed this artificial core, you turned it on and you start producing power. So you start sending energy into the rocky material of the planet. So initially the temperature of the surface might be very cold, and initially you might have H in, so the power going from the core into the planet, that might be greater than the power being radiated. And so then what would happen is that you would have energy building up in the planet. And so that energy would then cause the planet to heat up. Okay, so temporarily, you've got this situation where the temperature of the planet is changing. The temperature of the surface is then going to be increasing. And eventually, the temperature of the surface increases enough to where this outgoing radiation matches the power coming from the heater. And at that point, the temperatures stop changing because we've reached the situation where Hn is equal to H out. So today, what we're mainly going to be concerned about is a problem that's similar to this. We're going to be predicting the surface temperature of a planet, but it's not Yoltar's planet with its artificial core, the Ready Core 2000. It's going to be our planet. Okay, so it's very interesting that we've actually understood enough physics up to this point where we can make a prediction. Even without knowing the answer, we can make a prediction for what the surface temperature of the Earth should be. And that prediction will actually allow us to see what factors the surface temperature depends on. Okay. So here's the question that The planet, with a radius of 6,400 kilometers, lies at a distance of 150 million kilometers away from a yellow star with temperature 5,700 Kelvin and radius of 695,000 kilometers. And so we want to estimate the surface temperature of the planet. One additional piece of information that we're going to need is that the albedo, so this is defined to be the fraction of incident light reflected, that's equal to 0.37. So this is just taking into account the fact that the Earth is covered in, well, various materials, but in particular we have clouds covering a fraction of the Earth, and when the sunlight hits the clouds, it tends to reflect off rather than being absorbed by the Earth. So that'll be important for our later calculations. But we're going to take it a step at a time. And so first we are going to think about just the basic setup. So I've drawn a picture here. Here's the Earth. Here is sunlight coming in. Some of it's reflected off, but some of it's absorbed. And the orange indicates thermal radiation from the surface of the planet. Okay. So there's a key difference between this situation and the situation of Yoltar's planet that we just talked about. And that is that even though the core of the Earth is hot and it's producing energy through radioactive processes, most of the energy going into the Earth is just energy that we're absorbing from the sun. So we can basically ignore any energy that's being produced in the interior of the planet and just look at the H in as the energy from absorbed sunlight. Okay, so that is our H in this situation. The H out is going to be the same as before. We have some equilibrium surface temperature T that we're taking to be some average temperature that characterizes the whole surface of the planet. Obviously, that's going to vary over the planet, but in our simple calculation, in our simple model for the Earth here, we'll just assume that we have one single temperature. It's like an average temperature that characterizes the surface of the planet. Okay. So in order to predict that, what we're going to do is the same thing essentially that we did in the previous example. We're going to say that in equilibrium, in the steady state situation, that the power absorbed from the sun is equal to the power that the Earth is emitting due to radiation. And that will allow us to find the temperature. And actually, the only thing we kind of have to understand now is how do we calculate this H in? How do we calculate the energy absorbed from the sunlight incident on the Earth? Okay, so we're going to start piecing this together, and a good starting point is to think about how does the energy being absorbed by, say, a planet, which is a distance r away from the Earth, how does that energy kind of relate to the energy being produced by the sun? Okay. So in this question, H sun is the total power of the sun. It's equal to about 3.86 times 10 to the 26 watts. I'll explain in I think the next slide how we would calculate this if we wanted to calculate it. But for this question, it's going to be a given. So we're given the total power of the sun, and we want to know how much of that energy is going to be leaving this hole. So eventually that hole is going to be, we're going to think about that hole as being a hole that would be the size of the Earth. Okay, so we want to understand how much sunlight is absorbed by the Earth. But to get there, we're going to think about this question where we have a sphere surrounding the sun whose radius is r, and then we just want to know how much of the sunlight is going to go through this particular area, which is A. And I'll explain how that is relevant to the problem later. So this is just a problem to think about. So pause your video, read through the choices, and then we will talk about the answer. Okay. So for this question, the answer turns out to be D. And so let me explain the logic here. So the logic is very simple. The sun is producing energy at a rate h sun. That energy is electromagnetic radiation going out in all directions from the sun. So we could think of that expanding out in a sphere, or expanding out uniformly. Once we get to a radius capital R, then this radiation is spread over that entire area. Okay, so that area is 4 pi r squared. And so if we thought about how much energy is not going through the entire area, but going through just this particular area A, just the area of this hole, then we could say that a fraction, A divided by 4 pi r squared, that's the fraction that determines how much fraction of the total energy of the sun will come out. Okay, and so that's the logic, that we want to take the total power of the sun. Total power being produced by the sun is the same as the power of radiation going through this sphere, and the fraction of that energy going through the hole is just the fraction of the area of the hole divided by the area of the entire sphere. Okay, so that is summarized here. And so this will be very useful for us. So what we've understood just using basic geometry is that the power of light coming out through this hole is equal to h sun times A over 4 pi r squared. What we're going to be particularly interested in is something called the intensity. So that's the power per area. And so we'll take this formula, divide it by the area, and that will give us what we call the intensity of sunlight at the distance r. Okay, so intensity, it's watts per meter squared. And what we're interested in for our problem is, at the location of the Earth in the solar system, what is this intensity of sunlight? How much energy per meter squared is going to be going through a surface here? So I've just drawn a little 1 meter by 1 meter surface. It's basically at the distance of the Earth. And so this is the relevant thing for our calculation later of the incident energy from the sun. First, we're going to figure out how much energy from the sun is incident on a 1 meter by 1 meter region. And that works out, using our previous formula, to 1367 watts per meter squared. Okay, so that is basically just setting A equal to 1 meter squared, taking the power of the sun and dividing it by 4 pi r squared. Okay, quickly wanted to mention how we would get 3.86 times 10 to the 26 watts. Okay. So in our question, that was just a given. We took that value, we divided by 4 pi r squared, and that gave us the intensity of sunlight on Earth. But we could actually calculate the power of the sun, again, using our radiation formula. Okay. So if we wanted to, we could actually look at starting from the temperature of the sun and the area of the sun, which is 4 pi times the radius of the sun squared, using that the emissivity of the sun is very close to 1. We would just plug in those values in this result, and that's where the h sun equals 3.86 times 10 to the 26 watts comes from. Okay. All right, so let me just kind of summarize that. We could calculate this using the properties of the sun. Once we know the total power being produced by the sun, we can calculate the intensity of sunlight at Earth, which is the power per area, by taking that total power and dividing it by the total area of this giant imaginary sphere that would have the radius of the Earth. And that gives us that for every meter squared of area on that giant sphere, we have 1,367 joules per second going through that area. Okay. So For our later calculations, this number is just going to be an input into calculating the absorbed power of sunlight at the Earth. It's not really changing, so this thing, if you want to know what the intensity of sunlight at the Earth is for this problem or for any other problem, it's pretty much the same because the area of the sun and the temperature of the sun are staying the same. So you don't always have to go and calculate the power coming out of the sun each time you have a problem relating to sunlight. And so it's kind of very convenient just to be using this value, the I solar constant, and you could just use that as a starting point in many situations, as long as you're talking about intensity at the distance to the Earth. Okay. Next class will emphasize a lot that if you happen to be interested in Mars or Jupiter or Neptune, then you're going to have a different intensity because this 1 over r squared appears in the formula relating the intensity to the total power of the sun. Great. Okay. So going back to our original problem, our goal was to calculate the H in, which is the amount of energy per second being absorbed by the Earth from the sunlight. Okay. That was the missing piece that will allow us to complete our problem. So far now, what we have is the intensity of sunlight at the location of the Earth. Okay, so we know for a 1 meter squared surface perpendicular to the sunlight, that's how much energy there is. Now we want to say, using the actual size of the Earth, so little r is the radius of the Earth, and using the albedo, which is a fraction of sunlight reflected, how much total power is reaching the surface of the Earth from the sun? Okay, so pause your video and take a moment to think about that, and then we will talk about the answer. Okay, so all of these answers start with I solar constant. This is the power per meter squared of sunlight. That's if you had a 1 meter squared by 1 meter squared area perpendicular to the direction of the sunlight, that's how much power would be coming into that. To calculate the power absorbed by the Earth, we need to take into account how much area is the Earth blocking off of all this incident sunlight. Okay, so we kind of need to calculate, going back to this picture, we need to calculate the area of this part of the whole sphere that is blocked off by the Earth. Okay. Now there's various options for the area coming in here. 4 pi r squared is the total surface area of the Earth. 2 pi r squared is half of the surface. And pi r squared is the area of a disk that has the radius of the Earth. So clearly the sunlight is only being absorbed by one side of the Earth. Okay, so we might rule this one out immediately because the dark side of the Earth is not really relevant for absorbing sunlight. And we might think that this is the relevant area because that would be the area of the part of the Earth that is absorbing sunlight. But if you look at this picture, so this is a diagram showing the Earth and the sun rays, which are more or less parallel because the sun is very far away from us. What you notice is that the sunlight absorbed by a spherical body would actually be determined not by the area of half of that sphere, but really just by the area of this disk. Okay, so the amount of sunlight absorbed in this case is the same as the amount of sunlight absorbed in this case, where you have a disk which is the same radius of the Earth and arranged perpendicular to the incoming sun rays. Okay, so if we want to talk about how much area is the Earth blocking off out of that entire sphere through which the sunlight is going, then it's really just the pi r squared. It's really just the area of this disk that is relevant. Okay, so what we want to do is we multiply the intensity the power per area. We multiply it by the area of this disk, and that then is the total power of sunlight which is hitting the Earth. That's not quite our final answer yet, because we still have to take into account the fact that a fraction A of that total power hitting the Earth is going to be reflected. And so the actual sunlight being absorbed by the Earth is a fraction 1 minus A times the power hitting the Earth, which we just said is I times pi r squared. Okay, so the answer to this question is that the H in the total power of solar radiation absorbed by the Earth is equal to the solar constant, 1367 watts per meter squared, multiplied by this area, the area of the disk that is the area blocked off, the area of sunlight blocked off by the Earth, and then times 1 minus A, which is the fraction that actually makes it through to the surface and is absorbed. So now we are in really good shape because we have a formula for the absorbed radiation from the sun, and we have a formula for the radiation that's emitted due to thermal radiation based on the surface temperature of the Earth. And we're now able to make our calculation of the final surface temperature. So take a minute to try to do that on your own. Pause the video, and then I'll go through it. All right, so here we go. We'll draw the picture again. So we have H in, we have H out, and in the steady state situation, those have to be equal to each other. So now we're going to use our previous formula, the one we just understood in the previous clicker question. That's the energy per unit time that's being absorbed by the Earth from the sunlight. And that's going to be equal to the energy emitted by radiation. So A times sigma times E times T to the fourth. And here, what is this area? So basically, we have to ask what area of the surface of the Earth is actually emitting the thermal radiation. And the answer is that it's the entire surface of the Earth. So even though the temperature is not exactly the same everywhere on the Earth, it's pretty much similar. So in terms of Kelvin temperature, it doesn't really vary that much. And remember, T was the temperature that we're just kind of using as an average temperature over the surface of the Earth. Okay. So for the area here, we should be using 4 pi r squared because it's the entire surface of the Earth that the radiation is coming from. Okay. So we get pi r squared 1 minus A times I is equal to 4 pi r squared times sigma times E times T to the fourth. And it turns out that the pi r squareds cancel on both sides. And so if we rearrange this formula, then what we end up with is 1 minus A times I, solar constant, divided by 4 sigma E. And now we take the 1/4 power in order to isolate the temperature. Okay, so that is our result. That is our prediction for the temperature of the Earth, the surface temperature of the Earth, based on those various factors. Okay, here it is again. And so we see that it doesn't depend on very many things, at least in this simple model. It depends on the intensity of the sunlight. Okay, if the sun were more intense, then we'd have a higher temperature. It depends on how much sunlight is being reflected. So if our planet were completely covered in white clouds, then it would end up being that would mean that the A goes up, we'd end up getting a lower temperature. It depends on the emissivity of the Earth. Okay. And so this is actually a very interesting point. Okay, so what we're going to do now is actually calculate some numbers here. And first, what I'm going to do is assume that the emissivity is 1. Okay, and so this would be true if our Earth had no atmosphere. If we just thought about the surface of the Earth with the oceans and the rocks and the plants, and we asked, how good are those materials at absorbing infrared radiation? It turns out they are very good, and they would absorb almost all of it. Okay, so even though the Earth is blue and green and brown, in the infrared, it's basically a black body. It's basically black. It's basically absorbing all of the infrared radiation that hits it. Okay, so not accounting for effects due to the atmosphere, we can just set E equals 1 and see what we get. Okay, so I plug in all of these numbers. The A equals 0.3 has to do with the amount of cloud cover and the colors of the various things. That has to do with the amount of optical light coming from the sun that actually reflects off. That's where that comes from. So you plug all of that in with E equals 1 and you get T equals minus 18 degrees Celsius. So it's not way off. In Kelvin temperature, that's not so far off what we expect for the average temperature of the Earth. But generally speaking, the planet would be much less pleasant if this were the right answer. Okay, so our real temperature is significantly higher than that, even though there are some parts of the Earth where that might be the surface temperature. Okay, so where did we go wrong? And you probably already guessed it. I mentioned that when we set E equals to 1, we're ignoring effects to do with the atmosphere. So the reason why our Earth's surface temperature is not minus 18 Celsius, but instead a more pleasant positive temperature, is due to what's called the greenhouse effect that I'm sure you've heard about. So let's understand what that is. Previously, we assumed that emissivity was 1, and so that affects how much infrared radiation would be absorbed. But it also, more importantly for our question, it's coming into how much energy is being emitted by the Earth at the temperature of the surface. Okay. In the actual situation, we have an atmosphere, and the atmosphere contains what are known as greenhouse gases. So carbon dioxide is famous for this. What happens with the greenhouse gases is that some of the infrared radiation being emitted by the Earth, because it's at the temperature of the Earth, doesn't make it out into space, but rather is absorbed by these gases in the atmosphere. So it heats up, say, the carbon dioxide molecules in the atmosphere. Those things then partly radiate some of their energy into space, but partly radiate some of the energy back down to Earth. Okay, so that's what's indicated in the diagram. And so what happens is that if you have the Earth with its atmosphere at a certain temperature, then overall it is emitting less radiation into space than it would if there were no atmosphere and if we had the same temperature. What that means in terms of our formula is that there's an emissivity which is not equal to 1, which is actually equal to some fraction that depends on the content of our atmosphere. And so at the present time, the emissivity is around 0.6. If we plug that into our formula, then instead of getting minus 18 degrees Celsius, we end up getting a much more realistic temperature of around 14.5 degrees Celsius. Okay, so it's kind of amazing. Using the simple physics that we've learned, we're able to actually make a prediction for what the surface temperature of the Earth is, and we're getting a number which is completely reasonable. So of course on the Earth, we can just measure what the average temperature is. But this kind of analysis is particularly interesting for a few different reasons. One of them is that we could use the same analysis to predict what are the temperatures on other planets in our solar system, and also to make predictions for what are the temperatures of planets that we discover around other stars in our galaxy. So you hear in the news a lot about new planets being discovered. They're being discovered all the time around various planets. And sometimes you hear that certain new planets that are discovered might actually be habitable because their temperature is in the right range to support life. And so we're not actually measuring the temperature of those planets. What they're doing is measuring properties of the star, and they can deduce the distance from the planets to the star. And then using an analysis like we've done today, you can predict what the surface temperature of these planets around stars that might be 10 or 20 or 40 light years away. So that's an interesting aspect of this analysis. The other really interesting aspect of this analysis for our own planet is that we can understand how various factors might affect the average global temperature. Okay. So specifically, I told you that E was less than 1 because of greenhouse gases in our atmosphere. And one of the very interesting consequences of that is that if we were to increase the amount of those greenhouse gases, so say we add carbon dioxide to our atmosphere, we increase the concentration, this effect that I was just showing you is going to increase. More of the radiation will be absorbed, less will go out into space. And so as a result, the emissivity is going to be smaller as we make that increase in concentration. Okay. So increasing the concentration of something like carbon dioxide, according to our formula, will cause an increase in temperature. And this is the physical origin of the global warming effect. Okay. So if you look historically at carbon dioxide concentrations and you compare those to historical temperatures, both of these things are deduced by drilling down into the ice in the Antarctic and looking at properties of the ice. So you can correlate the carbon dioxide concentration with the temperature, and you see that it's very, very closely correlated. Okay, and so the reasonable explanation of this, based on our understanding today, is that as carbon dioxide increased, then that decreased the emissivity and that increased the temperature. So just looking at the data, all we can say is that there's a correlation, not that the increase in carbon dioxide increased the temperature, but based on our understanding of the physics of the problem today, that is exactly what the physics predicts, that increasing the carbon dioxide concentration would be responsible for that increase in temperature. Okay. And so the reason why everyone is so concerned about global warming is that if you look at carbon dioxide concentrations in the last 50 years and compare those to the historical levels, then they are just way higher. Okay, so this is like the last 400,000 years, the concentrations have varied between 180 parts per million and 300. And then just in the last 50 years, we've shot up to 400. So we're now much higher than these historical levels. We're seeing an increase in temperature. And so most climate scientists believe, and it's sort of very logical based on our analysis today, that this is causing this. And so there's this prediction going forward that if the CO2 keeps increasing, then the temperature is going to keep increasing. And that's why most climate scientists are saying that, well, we better do something about the carbon dioxide production rate. We better try to stabilize the level in the atmosphere. Otherwise, we risk these temperatures going higher and higher and causing all sorts of problems. Okay, so that's it for today. We'll talk more about this next time, and have a great weekend.